Another question on continued proportion. So they've given us here, what they've given us here is that if y is the mean proportion between x and z, we want to prove this statement here, x square minus y square plus z square upon x raised to minus 2 minus y raised to minus 2 plus z raised to minus 2 is equal to y raised to 4. Right. Now, just as we start now, let's use the first statement. Y is the mean proportion between x and z. So what that means is that x upon y is equal to y upon z. Right. Now, if you remember when we were discussing proportion, we were doing another sum there. Whenever we had two ratios equal, I guess in that sum it was a upon b is equal to c upon d. What we were doing is we were equating it to k and then saying a is equal to bk, c is equal to dk, right, and so on. So we could do something similar here as well, where we equate it to k and solve. But in the case of continued proportion, remember sometimes it's easier, instead of equating it to k, it's easier to use the equation. If I cross multiply this, I get y square is equal to xz, and making this substitution sometimes is easier than using the k substitution thing, right? So let's try it out with this. So for our proof, let's consider the left hand side first. Our left hand side LHS is equal to x square minus y square plus z square, the whole thing divided by x raised to minus 2 minus y raised to minus 2 plus z raised to minus 2. All right. Okay, so let's just deal with the terms in the denominator first. So we have x square minus y square plus z square. And remember, if we have a negative power in the index, or if we have a negative power, it means you have to take the reciprocal of the base. So x raised to minus 2 is nothing but 1 upon x square. Y raised to minus 2 is nothing but 1 upon y square. And z raised to minus 2 is 1 upon z square, right? Now, if you notice, what I'm going to do is, instead of the y square terms, I'm going to substitute xz, as we discussed earlier. So x square, now instead of y square, I'll write xz plus z square. That's our numerator here. And same thing in the denominator as well. Instead of y square, I'll put xz. So I have 1 upon x square minus 1 upon xz plus 1 upon z square, right? So this entire thing here is my denominator. Okay, now how do I simplify this further? There's nothing much to simplify in the numerator. However, in the denominator, what I can do is I can take the LCM so that all of them have the same denominator. Right now, x square, xz, and z square. The denominator would, the common term or the LCM for them would be x square, z square. So x square minus xz plus z square, this is my numerator, divided by, right? Now if I have to take the LCM of x square, sorry, if I have to take the LCM of x square, xz, and z square, remember the LCM for those terms would basically be x square z square, right? I have x square here, I would have to make this z square. I have xz here, I would have to get another xz. I have z square here, so that becomes x square, right? So this here would be my denominator. Now let's move the terms around. So this denominator of the denominator will move to the top, right? So rearranging the terms, this is x square minus xz plus z square into x square y square, sorry, x square z square, right, divided by, and this is z square minus xz plus x square. It can be rearranged into x square minus xz plus z square as well. So now if you notice, we have this entire term in the numerator, which gets cut with this entire term in my denominator, right? So all that I'm left with is x square z square, which can be written as xz the whole square. And if you guys remember, xz is nothing but y square. So y square the whole square. Now y square the whole square is y raised to 4. Therefore, our left hand side has simplified to y raised to 4. And if you notice the question, that is nothing but our right hand side, and hence we have solved our question.